Hi, everybody. It's a real pleasure to be back in Bilbao and see so many friends and colleagues. And I want to thank the organizers for putting together this very nice conference and to giving me the chance to speak about my work. This, by the way, the background image is the forest of Oma. It's like only 40 kilometers east from here in the Urdaibai Natural Reserve. And I found it very fitting to the conference topic. Like you walk around this forest and you see some painted trees, and depending on who you are, you may discover patterns in these trees that emerge. This talk is mostly based on this publication that I did together with Alex Monraz and Peter Wittig, which is also here in the audience, and it appeared last year. So it's titled Inductive Supervised Quantum Learning. Okay, I'm sure everybody here knows what supervised learning is. Mostly everybody will have an idea of what inductive supervised learning is, but we still will spend some time in narrowing this term down. But when I say quantum learning, I mean, we are still defining terminology, so it's, at the moment, it's rather ambiguous. So especially after hearing the roundtable on Monday, and in line with some of the comments that were made there, I decided to start with a disclaimer. So this talk will not contain speed apps. I will not present you any killer apps. I will definitely not develop any fancy home robot. And it will also not contain any QRAMs. I mean, even though these are very interesting problems and totally worth pursuing, I will not be concerned with those today. But rather, I will put myself in a fully quantum scenario. So what is also known as this quantum scenario that we heard about. And I will assume that the information is generally quantum, and I will take that as a given. So I will not give myself the ability to engineer classical data into a particular quantum state and then exploit this. But I will assume that it's just there. And the processing of this quantum information, obviously, is also going to be quantum. And then I will ask, or I would like to explore fundamental questions like, what does it even mean to learn quantum information? If quantum information is a quantum state, does it mean to learn the density matrix like in tomography, or a property encoded in this quantum state? And if you come down to a protocol or a task, and then you come up with an answer to this first question, then the second question pops up, and it's how natural is our standard machine learning techniques to learn in this quantum context? And these are very vague questions, so to run them a little bit, I will come to the very simple archetypical scenario, supervised learning for binary classification. So you all know this, okay, but let me just repeat briefly. I have my data will be just some vectors x in a real space, and I have two possible labels. Y can be 1 or 2. And I am given a training set, which consists in a bunch of vectors, x's with associated labels that are sampled from some unknown probability distribution that I don't have access to. Then I will be given a test set, so a bunch of other vectors that I want to attach labels to, and this is the task. So schematically, the algorithm works like this. So I input my training set, I do some training of it, and out of the training, I output a classifying function that will be used to associate new labels to the new test instances that will be given to me. And the archetypical example of this is, we heard yesterday about it, and this morning, the support vector machines. So yeah, I mean, you're given these two types of points, squares and circles, and then you kind of define this boundary in the middle, which will be the classifying function f. You apply this function to a new data point, and then depending on whether it falls to the left or to the right of this line, you associate a new label. Okay, so I will consider this problem in a fully quantum scenario, and for this, I will basically replace all the x's that I have by rows. So now my data will be quantum states in some complex Hilbert space. I still have two possible labels for them, and everything is the same. The schematics of the algorithm is the same as well. So I have a training part. Here it will be, in general, some quantum measurement performed over the training set. And out of this quantum measurement, I will get some classical information. I put this dashed line here to emphasize that this communication is classical. This is important because if this was not classical, then maybe it will not even be justified to talk about learning here in this context. Because again, what does it mean to learn exactly? You know? But if we forget about it for a while, and then we only focus on the task that we want to solve, which is to attach label 1 or 2 to this new density matrix that comes in, okay, in principle, if I'm in a fully quantum setup, this is not everything that I can do. I can do more general things. So the most general thing that I could do to solve this task is to put a black box here with quantum inputs and classical outputs and just do some complicated, entangled, coherent operation over all inputs that has these two classical outputs, okay? So this is a new thing that quantum gives us. And there's other crucial difference, which is that the training set now is of limited use. I cannot operate several times over the same training set. And then, okay, you can be more general, but then the question is, does it really matter? No? Do I have to go? I mean, do I get any advantage by going to this more general and potentially more complicated scheme? And I'm not the first person to ask this question. This question has been going on around for a little bit. As early as 2002, in the seminal paper by Sasaki and Carlini, where they considered a similar task, it was not classification, but template matching. And basically, all these works compare these two protocols. An algorithm that works in two separate steps, as machine learning usually works. Like I have a training step and then some task that I perform from information extracted from this training, versus a completely quantum coherent operation for solving the task, acting together on the training and on the test instances. And the thing is, this is what I label here by this C and Q. And the thing is, it seems to be very case-specific, depending on the setting you are, or even in the analysis that you do, if you're in a Bayesian setting or a more frequentist setting, and they're kind of contradicting results, if you consider pure states or mixed states or coherent states. So sometimes you do find a quantum advantage, or that's what these works tell you. So we were concerned about this, and we said, okay, how general is this? Because we want to make a really general statement about supervised learning in a fully quantum setup. Is it natural at all? So this is what we do in this work. And for this, let me begin by considering the classical case again, but from a very abstract perspective. So I will consider a learning protocol just by a stochastic map, which is this P here, that takes as inputs a training set, A, which I will not specify anymore what it is. This is going to be A for the rest of the talk. I don't need it. And then some test instances that I want to, say, classify if I'm doing classification. And then the stochastic map maps these inputs to a set of outputs, which will be the labels in classification, these Ys. Now, it's useful to define these marginal maps. So if I take this stochastic map and I sum over all possible labels but one, then I get the marginal map Pi. Okay? And then now it comes an important point, which is I will call a learning protocol inductive if it fulfills such a condition that it has the form of a non-signaling condition. So the meaning of this is that if I take this marginal map here, this Pi, and I exchange all test instances but one, so the xi here is the same xi as here, but all the others as primes, if the associated output that my learning protocol gives does not depend on this change that I just did, then I will call that my protocol is inductive. And yeah, two important things to highlight here is that even though I'm requiring this independence, each marginal map still depends on the training set A. This is going to be important for later. And just observe that such a condition includes the natural notion that we understand as inductive learning. So we take a training set, we process it, we induce a classifying function, f from it, and then this is the only thing that is applied to the tests to do the classification, no? It's this map here. So this is simply a more general formal definition of the standard notion of inductiveness. OK. Now I need a figure of merit to be able to say what is better and what is worse. And this figure of merit is normally the expected risk. So I have a risk function, which is this is 1 minus delta function, weighting the output of my stochastic map, and then I take the expectation value over this probability distribution peak xy. So basically counts how many times a test instance is mislabeled. And then I have the following lemma, that is, if I have an inductive learning protocol P in the previous sense that fulfills this non-signaling condition, then I can always find another inductive protocol. I mean, another inductive protocol that is factorized, that it has this factor structure. So this is just a product of stochastic maps. This is what I was saying before. I have an independent stochastic map acting on A that extracts classifying functions f, and this function f is acting as an input together with each single test. And this stochastic map Q produces new labels y. And I can construct such map, and according to this figure of merit, this excess risks, the two maps, the two protocols perform equally. This might seem all very trivial because, I mean, what else can you do in a classical setting, no? Than this. But we need this level of formalization to go to the quantum setup. OK, so in words, this lemma also tells you that every conceivable inductive learning protocol can be regarded as a two-phase operation. So I have a training step and then a test step. And by assuming this structure, I'm not losing any generality, okay? Any performance. Which also tells you that our definition of non-signaling condition is equivalent to inductiveness. This will all be not true in the quantum case. So let's go quantum. What I do here, OK, I have this underlying probability distribution that I want to learn. This is going to be replaced by a bipartite quantum state, rho xy. My classical stochastic maps P will be now quantum channels, which act on quantum registers, A and X, 1 to the n. Again, this is training, this is test. And outputs Y registers, which could be labeled if they're classical. But I'm not actually assuming that these output registers are even classical, OK? I will equivalently have some notion of non-signaling condition for these quantum channels. Don't worry about this form. So what I'm saying is that the most general quantum learning protocol that you can imagine, you can draw it like this. So I have this training set A, which in general will be some quantum set. I don't specify it, OK? And then I will have n copies of this unknown quantum state rho xy. I put in primes here because this register y prime will act as the true label if you want. And I'm going to send all true labels down here, this dash line, where there's only a referee. This is only for evaluation purposes. So the X part of the quantum state, I will send it up. I will put it as input as this, on this quantum learning protocol or this quantum channel. As outputs, I will have these y's. I will send the output y's down here, and then a referee will compare them y one by one, and it will compute some average risk. And notice that this is a very general scheme. So I'm not specifically talking about classification anymore. If you do classification, then what it means is that these quantum states rho xy's are quantum classical states. So I have a quantum state on the X part and then an associated classical register here containing the label But it also includes generative algorithms, as we were hearing in the talk by Jose Martin before. The X part could be a classical register, and based on this classical information, my task could be, OK, prepare some quantum state row Y, depending on this classical information. And yeah, OK. So I'm going to proceed. Again, I will not spend too much time on this, but basically, you have this symmetrized risk observable, which is going to evaluate your performance of your knowledge protocol, and basically you do so the same kind of argumentation. Like, if the risk observable is symmetrized, then I can also symmetrize my quantum channel on the X's, and then this will have no effect on my performance. And then a channel that factorizes, as in the classical case, that is reduced to marginal channels acting on each single test instance, will perform also equally. But there's a problem with that now. The problem is that each of these marginal channels acting on each of the X's will need a training set by themselves. And this is a nonlinear map in the training set. And we know there's something called the no-cloning theorem, so we have a roadblock here. And this could be the end of the story, but OK, it's not. You can actually come around this. How? The intuitive notion is that, OK, we cannot clone quantum states, but we can approximately clone them. So if we set ourselves in an asymptotic limit, we could say, OK, just measure the training set, extract some approximation of it, OK, just distribute this approximation over all the X's, and then act individually. Then the question is, how well does this perform compared to the global approach, unrestricted? And the formal result of the paper takes the form of a definitive theorem for non-signaling quantum channels. And basically, what it narrows down to this formula here, which tells you that the original unrestricted quantum learning protocol will have an X-6 EQ, and then I can come up with another one which is factorized in this sense. Like I have a separate operation in the training, and then equal local operations on each test, and the performances between these two protocols converge to each other when n is large, when I have many, many test instances. So basically, what it says is that you can take this picture, and if you impose this non-signaling condition on Q among the X's, then you can replace it by this picture, and you will not lose too much. OK? And just look that these are actually equal quantum channels based only on this training information. So it's really inductive in the previous sense. And with this finished, the take-home message is that despite quantum mechanics allows you in principle for much more, the two-phase separation between training and test that is so normally assumed in machine learning actually emerges naturally in a fully quantum context, if you impose this reasonable assumption of the channel being non-signaling, which, yeah. And so we just simplified as something that could be enormously complex to very simple one-way LLCC protocols. And this also extends trivially to quantum operations instead of quantum states, and it's not really important. And since I think I have no time. OK, then I will just leave the third point as a teaser if somebody wants to ask me in the question time or later in the coffee break. Thank you.
So thanks, Gael, for the really interesting talk. Maybe one quick question for Gael.
No signaling condition, in what sense you define the no signaling condition? Why did you call it a no signaling condition?
Why did I call it non-signaling?
Why?
It's kind of an independence condition on the X's, no? It's yeah, it's basically there is no correlations or correlations should not matter among the X's because you can replace them freely, and your assignment of a label will not depend on that. So basically, you have non-signaling among the test ports. Okay?
Let's thank Gael again.